In this lesson, we're going to look at falling bodies, specifically things that are falling in a straight line down, down. So we finished up the other time talking about this question: do heavier objects fall faster? And people had different ideas. Yes, heavy objects fall faster. Generally, that's what people think, if they don't really push themselves too hard to think about it. And this was certainly the way people thought about it throughout history. And then there's the idea that no, they all fall at the same rate, which is something that maybe we've been taught before. And then there's the idea, well, it depends. And I would say somewhere between those last two is really the reality of this. I have this, it's an analysis of free fall that you can look at that I put together. You don't really have to watch the whole thing. Taking a look at for your video analysis. As you see, it's also a tutorial on how to use this video analysis tool, which you can look at. But the basic idea is that if you watch an object fall and you can measure its position over time, you can put together a position, a velocity, acceleration profile, and find out what's happening. If we take a look at the question, right, of a ball and a piece of paper, we can watch what would happen if we were to drop a ball and a sheet of paper. If you drop a ball on a sheet of paper, this is just a half-folded sheet of paper, the ball clearly hits the ground first. Now, if I crumple up that paper into sort of the shape of a ball, so it's still the same ball, the same sheet of paper, what you see is something very different, right? You see that they both fall straight down. The paper doesn't bounce, the ball does. That's what you get. And so what we are led to believe then is that it's not the weight of the ball and the paper that matters. If anything, it has to do with how they're shaped. And this is really a question about air resistance. Usually when we talk about this in the United States, right, most of our history of science and physics and reason and literature comes from Europe. So we have this very kind of white Western Europe-centric view. But there's a very famous experiment. Well, it wasn't really... The experiment wasn't that famous. It is the public demonstration of it that was very famous. Galileo very famously dropped balls of different size and shape but different masses, similar size and shape but different masses, from the tower in Pisa, like the big plaza, and they landed at the same time. This wasn't his experiment. This was sort of his publicity stunt to explain it. He had done a series of experiments rolling balls down ramps of steeper and steeper heights in order to figure out kind of what was happening. And what he sort of came to was that the acceleration, when things were just falling straight down due to gravity only, if you could ignore air resistance, and that was a key thing, would be about 9.8 meters per second squared, or about 10 meters per second squared. You can actually do this. You can, put things into a vacuum chamber, and you can actually get rid of the air, and you could drop something like a feather and a ball. You can go back and watch this video. It's really interesting if you want to take the time. But even on a very large scale, it works if you can get rid of the air resistance. Right? So when it comes to the Earth and the acceleration due to gravity, we generally accept that around 10 meters per second squared is the value. There's a lot of things that can affect the exact value of it: latitude, elevation, where you are. There's that range. Usually we just say 9.8 or 9.80 if you need a 3 significant figure value and you're doing an experiment in the real world. But most of the time I just use 10 meters per second squared, and that's perfectly fine. The AP test, they don't care if you use 9.8 or 10. And 10 is a nice number for estimation, which is nice. So little g, this symbol, is the special symbol for the acceleration due to gravity. Often we use it as its own unit of measurement. If I were to say 1 g of acceleration, I mean about 10 meters per second squared. If I say 5 g's, I mean about 50 meters per second squared. We can also help you think about it. Can a car accelerate at 5 g's, 50 meters per second? That's very, very fast acceleration. That's more rocket and stunt plane kind of thing than car. So when it comes to the kinematics equations, we are going to be able to use them with little g because g is essentially a constant. And we said that we can only use the kinematics equations when we have a constant acceleration. And so that's what we're going to do. So here's an example, kind of a classic. You drop a rock from a tall tower. It hits the ground 3 seconds later. How tall is the tower? Well, we actually know everything we need to know to solve this problem because of some fundamental things about free fall. We, with our problem solving, draw a coordinate system called the starting point 0. We can call down positive x because that's the direction of motion. We want to know what the final height is, basically how far it fell. We know the initial height, we're calling it 0. We know the initial velocity, 0, because it was released from rest. We know the acceleration is little g, and we know how long it took. We're not given the final velocity, but we are not actually interested in that value. So we can pick our equation, x final equals x naught plus v initial t plus 1/2 gt squared. Notice we replaced the acceleration with little g. We have two values that start at 0, so we can eliminate those. We can plug in either 9.8 for the acceleration due to gravity or 10 meters per second squared, and we end up with approximately 44 meters, right? If you had left that as 10, we would have been 5 times 9, 45, but pretty close, okay? And so what would be different if we were to say, oh no, I like down to be negative, up to be positive, which is more our standard thing? Well, the only thing that would really change here is that, is that the little g would become negative 9.8 meters per second squared, and the final position would be 0, and the initial would be the unknown. That's all we would do there. So a couple of conceptual things that we can use to kind of estimate and make sure our answers make sense. If you, this is in page 29 in your packet, this is kind of a ball dropped. Well, you can very simply say, oh, well, if you release a ball, the initial velocity is going to be 0, and if there is no air resistance, the displacement will be 0 at the beginning, and we can just use little g. So if we call up positive and g is negative 10 meters per second in this case, we can go through and solve these problems. Every second, it picks up speed by 10 meters per second in the negative direction. And the displacement can be found by using that kinematics relationship we just looked at on the previous slide, in the previous example. So after 1 second, it's gone 5 meters. After 2, negative, it's gone 20. After 3, 45. And after 4, 80 meters. And this is actually really powerful. It may not seem it now, but the idea is that it doesn't matter what you drop. As long as you can ignore air resistance, which is a good first approximation, you can always get these answers. The other thing that's interesting here is that we have sort of this law of odd numbers stuff because we have the squared time piece, which gives us those values. 1, 3, 5, and 7 are the relationships between in the spaces there. You could also do this on the way up and then back down. This is still free fall, even though it is not falling. It's just that the initial velocity is something upward, and then we go up to the top. There are a few things we know about this. To get to the top, you must get to a speed of 0. So at the top, the velocity is 0, right? And at the bottom, the position is 0. So if we look at the falling part, the second half of the motion, it's exactly what we would expect. And on the way up, we're going to mirror that because it takes the same amount of time, 4 seconds to go up as it does to come down. And every second you change your velocity by negative 10 meters per second. Then we can go ahead and fill in the values, right? We go down by 5, then 20, then 45, then 80. So that means the top is 80. And we can fill in the graph. And it's nice and symmetric. And this is something we can use to solve problems. It's useful to estimate. It can be really helpful to know that g is about 10 meters per second squared, and therefore, when defining down as negative and up as positive, g would be negative 10 meters per second squared. This makes estimating really easy. For example, if at time t equals 0, you throw a ball up in the air and it takes 1 second to reach its highest point, we can say a lot of things. After 1 second, it has to be traveling at 0 meters per second. After 2 seconds, that's 1 second later, it's now traveling down at negative 10 meters per second. And after 6.7 total seconds, that's 5.7 seconds after it reaches its highest height, it would be going down at 57 meters per second. If you go all the way back to the beginning at 0 seconds, 1 second before it got to the top, we'll be going up at 10 meters per second. Now that we have some of the estimation down, we can solve a bunch of free fall kinematics problems. So in free fall, known as touching, pushing, pulling in the object only gravity, A is equal to G, and so that's a known quantity. So for example, a ball is thrown straight up and goes to the ground in 5 seconds. How high does it go? Well, we can use the fact that up is positive and we have 0 height at the bottom, as well as some of those things. We know how much time it takes. And we don't know anything about the initial and final velocities, but that's okay. We can relate those quantities. Or do we know them? Well, if we consider that at the top, it's at 0 velocity, we can call that the starting point or the ending point. And so if we cut the problem in half the time takes us to the top and half the time brings us down, we could say the top is our 0. We want to know how far it falls. We now know the time and the initial velocity and the initial position and the acceleration. We can go back to our favorite equation and find that it fell 31 meters, or in other words, the maximum height was 31 meters. If we wanted to know its initial speed, well, similarly, we're going to use half our trip again. We want to find the final velocity. We know the rest. The initial velocity is 0, and we can solve for the final speed, 25 meters per second at the bottom, which is 25 meters per second up at the very beginning and 25 meters per second down at the end. So does that make sense, right? We have a symmetry. It has the same speed up and the same speed down at the beginning and end, but the velocity is different because the direction is opposite. We can also use the whole trip if we wanted to, right? We do know something about this. We know the initial and final velocities are equal but opposite in direction. So we can use V final equals V initial plus GT, divide through, and we end up with that same thing, 25 meters per second. There are a few other videos you can go back and watch this free fall on the moon. This is from the Apollo 15 moon mission, a hammer and a feather. It's a fun one to watch. You can also go back and watch the big vacuum chamber or my tutorial on graphical analysis and so on. But the big deal is that free fall problems are really just kinematics problems with constant acceleration up and down. So use that fact, and we will talk about this more